kids. We have a lesson today that has a very simple calculation, but a little bit of a trickier conceptual understanding, but it's going to be very important for the next few lessons. So take your time and go through it, listen carefully, and ask questions when we get back together. Please do this problem. Excellent job. You took 9.8 meters per second squared. That's gravitational acceleration on Earth. Divide by 6, you'll get 1.6 meters per second squared. Forget about that for today. We're going to talk about electrical fields. We've talked about gravitational field before, but I'm going to make it even simpler. Let's talk about temperature fields. A field just means you look at an area, some space, and you describe something about that space, something about every point in that space. So let's say my space is just my living room, or a living room, hypothetically. Let's say there's a door here, there's two windows here, let's say there's a radiator here, a TV here, a computer here. I made it up. If I went into my room with 1,000 little thermometers and I put them all over the room, and then I measured the temperature at every point, and I just wrote the temperatures. So basically, I take a map of my room, and all over the map, I write the temperature at that point in the room. That would be a temperature field for my room. So it describes the amount of heat in all parts of the room. I'll get different numbers in different areas. Like I'll get a high number by my radiator, that's where the heat comes from. I might get a lower number by my windows because they might be open or they might not be insulated, heat will escape. My TV computer might be a little hotter than the outside. If there's like a water pipe going under the floor, then you'll see that in the temperature field, but you won't see it in the room. But temperature field. It doesn't matter why the temperature is what it is. All you care about is the reading, the temperature, the physical measurements, the factual values. So that's temperature field. It measures or describes how much heat is in every area of the room. Forget about that. And forget about G is 9.8 meter per second squared. This G is 9.8 newtons per kilogram. We saw this equation many times. This is not acceleration. It's gravitational field strength. So here I have, and I'll read it like this for no reason. Okay, so let's say I'm on Earth's surface, which I am approximately. I'm very close. If I have like a 2-kilogram rock on Earth's surface, its weight will be about 20 newtons, 19.6 newtons. If I have a 1-kilogram Tibetan singing bowl, also on Earth's surface, then its weight will be not 19.6, 9.8 newtons. Okay. So no matter what you put on Earth's surface, the mass, 1 kilogram, 2 kilogram, and the weight, 9.8 newtons, 9.6 newtons, are related by this formula. Great. What happens to G, the gravitational field strength, if I went higher and higher and higher and higher and higher, and eventually up into space? What would happen to G? If you think back to the formula that we talked about last lesson, Fg equals G m1 m2 over r squared, Fg will get lower. If Fg is decreasing and m is constant, little g, the gravitational field strength must be decreasing. So if I take my rock and lift it higher and higher and higher, I'll eventually reach a lower g. Instead of 9.8, I might go to 9.7, 9.6, 9.5, 9.4. And then I'll get up into deep space. And if we go far enough in deep space, far from any planets and stars, and comets and asteroids, whatever, there'll be no gravity. Okay, that's cool. Got it, babies? Yes, Mr. Lamb. Makes total sense. Perfect. Great. Good job. So for all these objects, this equation is true. What about this other object? I have it hidden right over here. This is a very special physics object. Here it is. This object in my hand has very special physics properties. We're going to use this as an example. What if this object right here was on Earth's surface? What would its weight be? It's nothing. Nothing. I'll put nothing right here. What's the mass of nothing? 0 kilograms. Okay. So, right here, I put nothing on Earth's surface. The weight of this nothing, 0 times 9.8, 0 newtons. It does fit the equation. It does work out. So, let's look at some interesting things. This rock is on Earth's surface right now. Its mass and weight are related, like so. If I brought it to deep space, what would the force on the rock be due to gravity? If it's in deep space with no gravity, then the force of gravity is also 0. So even though it's not totally true, we can use it as an approximation. We can say there's no gravity in deep space. Alright, I put nothing on Earth's surface and it experiences a force of gravity of 0 newtons. Does that mean that there's no gravity on Earth's surface? What do you think? There is gravity, Mr. Lamb. Yeah, that's right, Daisy. But there's no force of gravity. It doesn't matter. There's still gravity fields. Wow, real smart. Just like you guys too. Gravity fields, the reason I went over this whole thing is because gravity field doesn't depend on the mass. We could list the weight of every object in the whole Earth. 0 newtons, 10 newtons, 20 newtons. It doesn't matter. But that's silly because they all obey this equation. So, for any object on Earth's surface, if we know the mass, we know the weight. And if we know the weight, we know the mass because it matches this formula. Fg over m equals g. Okay. So that's the gravitational field around the Earth. It's 9.8. Over here is 9.8. Over here is 9.8. Over here is 9.8. Over here is 9.8. If you get farther out, you might see 9.7, 9.6. But no matter where you are, this equation will tell you G. If you're confused about this, please ask me in class. Why did I show this? you can have gravitational field without a mass. So for the temperature fields, that's kind of weird because you can't have no temperature. You can't have, well, I mean, you could have absolute zero temperature, but you wouldn't have it in your house. You can have no, you can't have no temperature. Every spot has a temperature. For this example, every spot on Earth's surface has the same gravity field strength, 9.8, 9.8, 9.8, 9.8. It doesn't matter what I put there. I can put a rock there, I can put a Tibetan singing bowl there, or I can put nothing there. If I put nothing here on Earth's surface, then G will be 0 newtons over 0 kilograms. And you might say, oh, 0 over 0, it's undefined, so just write undefined and give it to your math teacher and you get 100. Yeah, that's true, but this is not a math problem, it's a physics problem. This problem is saying, how strong is the gravity over here on Earth's surface? The gravity has a strength of 9.8 newtons per kilogram. It doesn't matter if there is no mass over here. You can still say the gravity's strength over here on our surface is this amount. And that's true all over the solar system. So let's do two strange examples. Here's the Earth. Let's say we got the moon over here. Let's say we got Jupiter over here. Again, not drawn to scale, not drawn to scale. As we saw, the moon has weaker gravity. On the moon, G is about 1/6. It's about 1.6 meters per second squared. On Jupiter, G is about 2.5 times as much. G is about 25 meters per second squared. Okay, I'm kind of repeating myself, but it's really important. So, let's say I weigh 100 kilograms. If I'm on Earth, then my weight would be 980 newtons. This sounds kind of stupid, but it's going to be relevant later. If I were on Jupiter, my weight would be 2,500 newtons. If I were on the moon, my weight would be 160 newtons. But I'm not on Jupiter, and I'm not on the moon. That doesn't mean the moon and Jupiter don't have gravity. They still have gravity. They have a gravitational field. So, if my 100 kilogram mass is in Earth's gravity field, my weight would be 980 newtons. If my mass were in Jupiter's gravity field, it would be 2,500 newtons. If my mass were on the moon's gravity field, it would weigh 160 newtons. Anyway, gravity field, the mass doesn't matter. If I found a lighter person who was only 50 kilograms, the same equation would work. That's why we divide by mass. So that was a whole long explanation. The point is, you divide by mass, then mass doesn't matter. Sorry for taking so long. Let's move on. Divide by m. So m doesn't affect g. There's one last thing. For temperature, we could just use a number. The temperature over here is 40, over here is 50, over here is 60 degrees. On Earth, for gravity fields, we could use numbers, but a number is missing one important piece of information. Temperature doesn't have this, but gravity field does. Gravity does. So what does gravity need that temperature doesn't have? Tell me now. What's that? Oh yeah, I heard you. Great job. It is direction. Gravitational force is a vector. Gravitational field is also a vector. Those are gravity field vectors. Temperature wouldn't have this, but gravitational field does, and electric field does too. So let's actually talk about electric field now. Test. Okay. Okay. So pretty simple setup. I have a plus 5 Coulomb charge. I have 3,000 meters, 3 kilometers of empty space. And 3,000 meters from that charge, I have a point P. I call it point P because point starts with P. So first, some calculations. Let's pretend I put a charge there at point P. Not 5 coulombs, another charge. If I put a charge at point P, what force will it experience? What force would it experience if I put 1 coulomb, 2 coulombs, or 3 coulombs? Fill in this table using the formula Fe equals K Q1 Q2 over R squared. Let me do it, Mr. Lamb. Okay, sure. We're going to use K. What's K? Well, it's normally 8.99, but let's round to 9 times 10 to the ninth Newton meters squared per coulomb squared. Okay, Hazel, sure. So, 9 times 10 to the ninth divided by 3,000 squared. Ooh, these numbers work really nice. It's almost as if they were planned. 9 times 10 to the ninth over 3,000 squared. This is 3 times 10 to the third. So 10 to quick math. 5,000 newtons. 10,000 newtons. 15,000 newtons. Excellent job by. Oh, that was Hazel, not me. Okay, amazing job. Do you guys see the pattern? Oh wow, yeah, I know. Fe over Q always fits the same ratio. At point P, Fe over Q is always the same value. 5,000 newtons divided by coulombs. 5,000 newtons per coulomb. This is known as the electric field strength at point P. No matter what charge you bring to point P, the force experienced by that charge divided by that charge will always be 5,000. 5,000 newtons per coulomb. It doesn't matter if it's a positive charge or a negative charge, and it doesn't matter if the charge is 0. if I put 0 coulombs of charge, like a neutral rock, at point P, it will experience no force, 0 newtons of force. The math doesn't really work out, but it worked out for all the other numbers, so we just pretend it works. 0 newtons over 0 coulombs is 5,000. It does work if you expand it out across multiply. Fe equals EQ. Oh yeah, that works. 5,000 times 0 coulombs does equal 0 newtons. So yeah, we're good. Just pretend that never happens. Just go with this. Fe equals E times Q. E is the electric field strength. It's just a number you multiply by Q to find the electrostatic force on that Q. No matter what the Q is, it works. Assuming you're at point P. If you were over here, or over here, over here, any other point, like point Q, point R, point S, every point has a different electric field. And we'll come back to that in a second. But that's the idea for electric field strength. If you wanted to, you could realize that, oh, K Q1 Q2 over R squared equals EQ. And the Q's, you just cancel. So yeah, that kind of works. As long as the Q you cancel is the one over here, not the one over here. The Q that cancels, remember how we said it doesn't matter what that Q is? It could be anything. It could be 1, 2, 3, or 0. So that Q doesn't matter, so we give it a special name. We call it a test charge. So I'll explain some class if you're confused. Please bear with me. The test charge is a small imaginary positive charge. You imagine that there's a small, tiny positive charge somewhere in space. You find the force on that charge, if it were there. Then you divide by that charge to find the electric field. Because you divide by the test charge, it doesn't actually matter what the test charge was. You can still find the electric field at that point, point P, from the formula. But if you see this symbol, that means a test charge. It's a small imaginary positive charge. It doesn't have its own field. It's just something physicists imagine when they're describing the field around something else, when they're drawing the field around a big 5 coulomb sphere. Or anything else, doesn't matter. Kind of like the thermometer. The thermometer doesn't have its own temperature. It doesn't affect the temperature in the room. It just measures it. This, physicists are imagining there's a test charge. They're imagining a charge is there. We measure the force on it. Then you divide by the charge to find the field strength at that point. Okay. So last thing. I said that I found the field strength at point P, but there's lots of other points in the world, like point Q, point R, point S. Yeah. The field describes a space. So this whole area is the space. You could mathematically calculate the electric field at every point and write it in a number, but that's not super useful. What is useful is drawing the field around an object and looking at it and knowing what will happen to charge if it's allowed to flow. It's kind of hard for me to think of examples right now. But if you guys ever see like old TVs, not flat screen, but like the big TVs, or if you see like like a power grid, the transformers and the power lines and stuff like that, a scientist might want to know the electric field around them because there's going to be a lot of charge flowing, and they want to see what the charge will do. So they'll take their knowledge of electric fields and make an electric field diagram. So here's point P. We found earlier that the electric field strength at point P was 5,000 newtons per coulomb. But there's more to it than that. If I put a positive charge at point P, a small positive test charge at point P, it will experience a force. The force will be 5,000 times Q, the charge. But the direction also is important. If Q is a small positive test charge, Q naught, it'll be repelled. So we can draw it like this. So the electric field at point P is this. Not 5,000 newtons per coulomb, 5,000 newtons per coulomb to the right, because it's a vector. Let's say there's another point Q, same distance from the positive on the other side. Well, if you think about it, you tell me, what would the electric field at point Q look like if it's the same distance from the positive on the other side? It would be the same magnitude, opposite direction. But that's the field. The number is not important. If you want to analyze the field, it's kind of like a graphical thing. It helps to visualize. We don't care about the numbers. A field is a description of something at every point in the space. It's not temperature, it's not gravity. This electric field diagram is a diagram showing the field at every point. We show the direction of the field with an arrow. And we show the strength of the field. There's multiple different ways, but let's say we show the strength of the field by the number of arrows. So close to the positive, we have a lot of arrows. And then the farther away you get, the fewer arrows you draw. There's other ways to do it. Some people draw bigger arrows for stronger field. Some people draw thicker arrows for stronger field. Some people draw darker arrows for stronger field. But I did more arrows. It doesn't really matter what you do. I can look at this picture and I know exactly what's going on. I can look at the picture and say, oh, no matter where I put a positive charge, it'll be repelled from the center. And the repulsion is stronger the closer to the center you are. That's what I can see from the diagram. I don't even need to know the charge in the middle. The diagram tells me what would happen to any positive charge I put anywhere in this area. And it doesn't matter to me what charge is actually causing it. All that matters is the field caused by that charge. This also tells me what happens to a negative charge. If I put a negative charge anywhere in this area, I know it'll be attracted to the middle. Because a negative charge would give me the reverse, a negative force. So I just flip direction. So no matter where I put a positive charge, it'll be repelled by the middle. No matter where I put a negative charge, it'll be attracted to the middle. Excuse me, to the middle. And the force of attraction or repulsion I could find from the formula if I knew the field at that point. The field is not always 5,000. It's stronger here, weakest out here. That's an electric field diagram, which is another interesting idea in physics. You don't really see too many like AP questions about drawing them or understanding them, but they are pretty useful for something we'll talk about in a few units. So let's say I have an interesting setup. I have 4 charges. And I want to draw the field around these 4 charges. Well, near the positives, it'll be going away. Near the negatives, a field is the direction of force on a small positive charge. So the field is toward negatives. It's a little abstract, but you have to imagine you had like a big handful of positive charges and just kind of threw them out onto the board. Draw an arrow pointing which way they'll all go, or which way they'll all experience force. If you do that, that's an electric field diagram. So if I drop a positive charge right here, it'll be repelled by this positive, attracted to this negative, it'll go like this. If I put a positive charge right here, it'll be repelled from this, attracted to this, it'll go like this. And so on, and so on. So this is a field diagram. It shows the direction of force on a million imaginary positive charges that are just sprinkled all over the place. Those charges aren't actually there, but if they were, this is the force they would experience. There's a lot of analogies people give. I used to think of this as like a swimming pool. And you know, a swimming pool, they like to like recycle the water. They like suck it in some vents, and they clean it, and then they pump it back in some other vents. So this is like the outlet where the water comes in. The water comes out, swirls all around the pool, and then goes into the inlets. So water comes out, goes in. The water is moving all over the place. The motion of the water is the electric field. It's really strong near the vents and much weaker far away from the vents, but it always shows the direction the water will flow. I'll show some more examples in class if you think that'd be helpful. But this is the very important concept, electrical field. What else do I want to say about electric fields? Not much for now, because I know you might be slightly overwhelmed. But we'll see some pictures and examples later. Electric field is like an imaginary property of the space around charges. The closer you are to the charges, the stronger the field. The stronger the charges, the stronger the field. And the direction of the field is away from positives towards negatives. So we'll draw some examples and calculate some examples in class. Hopefully you can ask me questions then.